All right, hi guys. So in this video, I am going to talk about solubility curves. All right, so you guys have learned hopefully a lot about solutions, the solutions vocab yesterday. So kind of like some big high points from that should be that hopefully you guys learned the definition of a solute and a solvent. So solute is what is being dissolved, whereas a solvent is what's doing the dissolving. We're going to be focusing kind of more on like the basic definitions and like how those solutes and solvents are affected by outside environments and things like that. But so for this day, we're going to talk about the solubility curves, which a solubility curve is basically a representation of how much solute can be dissolved in a solvent based on what temperature our like solution is made at. Okay, so first thing we need to talk about though is what is solubility. So you guys, if you remember way back to our chemical reactions unit, it's where we first talked about solubility rules. And when we talked about those solubility rules, we basically talked about can something dissolve? All right, will something dissolve? And that's all we said that solubility was. Solubility is the ability of something to dissolve, and that is still true. But it's not only just like the ability of something to dissolve, but it's also how much will dissolve. So in this unit, when we're talking about solubility, yes, we're still talking about can something dissolve, but we are also going one step further and talking about, well, how much can it dissolve at a specific temperature for solids. So solids is temperature dependent only, and then temperature and pressure for gases. So our definition of solubility for right now is the maximum amount of solute that can dissolve in a given amount of solvent at a specific temperature. That's true for everything, and pressure. And pressure only relates to gases, and we'll talk about that in a little bit. So how much solute can dissolve in a certain amount of solvent at a specific temperature and pressure to form a solution. And so one way that we can actually determine this is we can look at what we call a solubility curve. All right, and a solubility curve, basically, I'm going to scroll down real quick to show you guys. So this is a solubility curve. A couple of things you guys may notice about it is that number one, there's a lot of substances on there. This is like a pretty standard solubility curve. This one is probably the most used and the most seen solubility curve. So you guys will probably use this one a lot to answer questions. But you can see there's a lot of different substances on there. They're all labeled. All right, a couple other things I want you guys to point out to you guys is that our x-axis is temperature. All right, so how is my solubility affected by temperature? And our y-axis is grams of solute per 100 grams of water. So we do have a specific amount of solvent that we're looking at here too. It's not just general. Okay, so that's kind of what our curves look like. So what is this telling us? So you guys saw there was a lot of curves on the graph. So each curve represents the solubility for each compound in 100 grams of water. So it tells me basically how much of that substance can I dissolve in 100 grams of water at that temperature. All right, so how much can I dissolve? All right, and if we look at our graph again, you guys will see that there are some lines that go up, that increase as temperature increases, and some that go down, some that decrease as temperature decreases. As temperature increases. Words are hard. So you'll see that there's some lines that are going up. In fact, most of them are going up, while some are going down. Now then, the difference between these two is generally state of matter. So solubility of most solids is going to increase as temperature increases. So the higher the temperature, the more solids dissolve. All right, I always think of like hot chocolate. So if I'm making hot chocolate, all right, if I heat up my water, it's so much easier to dissolve my hot chocolate powder than it is when I like use room temperature water. So solubility of solids increases as temperature increases. It's easier to dissolve. We're from the South, so if you make sweet tea, you also probably know that it's a lot easier to dissolve the sugar when the tea is hot versus when it's cold. So that's with solids. But with gases, the solubility of gases decreases. Oops. If I can spell, that would be awesome. But yes, solubility of gases decreases as the temperature increases. And guys, I don't know if this has ever happened to you. It's definitely maybe happened to me once. But if you go and like buy a bottle or a can of soda in the summer and you leave it in your car, all right, guys, there's a good chance that that can of soda is going to explode. All right, and the reason why is because the solubility of gases is going to decrease as temperature increases. So as that soda gets hot, the gas is like coming out of the solution. It's undissolving, which causes the pressure to increase, which then can make your soda can explode all over your car, which is so fun. But yes, so solubility of gases decreases as temperature increases. Now on our graph, obviously, there's a lot of space above and below the curve. So we kind of need to talk about what that means as well. So the curve itself actually tells us when a solution is saturated. So I'm going to come define that right down here. All right, so a saturated solution, the very like basic definition that I can give you of a saturated solution is that it is full. All right, it's full. And so what that means is that we have dissolved the maximum amount of solute. So we've dissolved the maximum amount of solute. Our water or whatever our solvent is can't hold anymore. You guys may have seen this before. If you were like a kid, when you were a kid, you might have done this. If you like were making lemonade or Kool-Aid or whatever, and you have to add sugar to it, sometimes you may have added so much sugar that no matter how much you stirred, there was still sugar at the bottom of your solution. So that means you've made a saturated solution. Now, if you add more water, that sugar will eventually dissolve, but you've added so much that you have like that solid layer down there and no more can dissolve. So that's a saturated solution. Completely full. There's no more like room for any other solute to dissolve. Now then we have two other types of solutions that we can make as well. So if we're above the curve, we have made a supersaturated solution. And I'll tell you guys about that in just 1 second. And then below the curve, we have made an unsaturated solution. So in an unsaturated solution, it is not full. So basically, we have not dissolved the maximum. I'm going to put dissolved on this next row instead. Not dissolved the maximum amount. So we haven't dissolved the maximum amount. There's still room. You can add more and it would still dissolve. Okay. And then supersaturated is what we would call over full. Over full. So in a supersaturated solution, there is more dissolved than the maximum amount. So you may be asking, well, how does that work? How can you dissolve more? All right, and guys, typically to make a supersaturated solution, what you would have to do is you would like heat your water up. All right, so you would heat it up and then dissolve your solute in it, and then let it cool. And as it cools, that solute's not going to come out of the solution unless it's disturbed in some way. All right, and so yeah, heat it up and let it cool. You guys will see we're actually going to post an optional lab for you. It's really like it's optional. You don't have to do it, but it's kind of fun since we can't do the ice cream lab just since we're not in school right now. We thought this might be kind of a fun one for you guys to do, and it's the rock candy lab. In the rock candy lab, you are essentially going to dissolve more sugar than you can in a solution and then let it like sit. I think it's maybe even like 12 to 24 hours. And you guys will see that it'll like crystallize out because it's a super saturated solution. So that's going to be kind of a fun lab. I also will post a video of a super saturated solution for you guys to see as well. So let's talk about what happens now if I add a crystal to each type of solution. So when I'm talking about adding a crystal, like if I had sugar dissolved in water, and that's what I'm talking about for each of my solutions, what would happen if I added like one more piece of that sugar or one more piece of that salt, whatever your solute is. So for an unsaturated solution, if I added one more piece of like sugar to that solution, one more piece of solute to that solution, all right, it would dissolve. It should dissolve. All right, it should dissolve, no problem. And you'd be one step closer to having a saturated solution. Now then, and unsaturated will continue to dissolve until it becomes a saturated solution. Now then, with a saturated solution, if I add one more piece of that solution, it should collect at the bottom. It will not dissolve unless you manipulate it. So adding stuff to the bottom does not make it a super saturated solution. So like having sugar at the bottom is not a super saturated solution. That is a saturated solution with undissolved solute at the bottom. It's not super saturated if it's collected at the bottom. It's only super saturated if it is actually dissolved. So it just like basically collect at the bottom if you added more. Now then super saturated is where it actually gets cool. So in a super saturated solution, if I add one more crystal to it, it'll be kind of like what we call it'll like come out of solution. So it'll undissolve essentially, and it forms this like really cool crystal. And it's really cool to watch. So this, I don't know if you guys have ever seen them, but there's these hand warmers that are reusable. Right? And they're mostly super saturated solutions. But basically, it's kind of like this jelly substance, and there's a metal disc. And when you break or bend the metal disc in the center, it causes the hand warmer to like solidify, and it gets warm because it's an exothermic process. And so it's like really cool. But I'll also post a video of a super saturated solution on Canvas for you guys to watch as well. So you can see what happens when you add one more crystal, because it's really cool to watch. But yeah, and that's how they make like rock candy for sure, is made through the super saturated solution, which is why we have that lab for you guys to do. Okay. So now that we've kind of talked about what is solubility, what do the curves represent, what we're going to talk about now is how do we actually read these curves. So most solubility curve questions are all about just reading a graph. So if you can read a graph, you're going to be just fine here. All right, it's just important that you know what it's asking and know those few things about like on the line is saturated, above is super saturated, and below is unsaturated. So what we're going to go ahead and do right now is we're going to talk about how to read this graph. All right, so our first question wants us to, and I'm going to do them in different colors because I'm going to make dots on the graph and stuff. So hopefully it'll kind of make it easier for you guys to see. So our first question wants to know, what is the solubility of KNO3 at 50 degrees Celsius in 100 grams of water? Now, for the most part, we can kind of ignore that 100 grams of water as long as it matches with what I have on my y-axis of my graph. We'll kind of talk about that more in a minute when we get to one that doesn't say 100 grams of water. All right, so we're going to go ahead and come over here, and I want to know the solubility of KNO3 at 50 degrees Celsius. So first thing I'm going to do is I'm going to find 50 degrees Celsius, and then I'm going to find where KNO3 is, like where it intersects with that 50 degrees Celsius. And it's right there. All right. So when it's asking what is the solubility, it wants to know how much can dissolve. So at 50 degrees Celsius with KNO3, we can dissolve 80 grams. Because of just got that from what the point I am at on my graph right there. So 50 degrees Celsius, KNO3, 80 grams. All right. Now then our next question Oh, I wrote that in the wrong spot, didn't I? Let me rewrite that. Okay, so now then for our next question. It wants to know how much NH4Cl can dissolve in 100 grams of water at 90 degrees Celsius. So once again, that 100 grams still matches the amount on my y-axis. All right, so now let's do NH4Cl. So I'm going to zoom in on my graph again. All right, I'm looking at 90 degrees Celsius, and I'm looking for NH4Cl. So at 90 degrees Celsius with NH4Cl, I can dissolve 70 grams. Again, just reading a graph here. All right. Now then, for this next one, we are looking at a specific point. So it's giving us kind of two data values on our graph. So we're going to kind of go to both of those data values together and like see which solution it is or which substance it is. So it wants to know which solution is saturated when 20 grams of this solute is dissolved in 100 grams of water at 65 degrees Celsius. All right. So I'm looking at 20 grams of solute at 65 degrees Celsius. That's right about at that point on my graph. All right. So 65, 20. And which substance is saturated? So which one basically, which line am I actually, is my dot on? And right now my dot is on ammonia or NH3. All right. Now it wants us to name the gases on our solubility graph. Well, one thing we talked about earlier, if you guys remember, is we said that the solubility of most gases is going to decrease as our temperature increases. So when I'm looking for which are my gases on my graph, I'm looking for whose solubility is decreasing. So in this case, looking at my graph, I can see that NH3 solubility is decreasing, and then Ce2SO43, its solubility is decreasing as well. So those are going to be my two gases. So NH3 and Ce2SO43. Okay. So now, next question, and then I'm going to have you guys do like the last like 3 as practice. And then I'll put the answers up. So next one I'm going to do with you guys. All right. So this one says, how much KClO3 can dissolve in 200 grams of water at 0 degrees Celsius? Now, this is where it's important that we look at our graph. So my graph is only at 100 grams of water. All right, so basically what we're going to have to look at is if that's how much can dissolve in 100 grams, then how much should be able to dissolve at 200 grams. So let's start just like first off, let's just start with figuring out how much can dissolve at 100 grams. So at 100 grams, I can dissolve about 5. So you can do it a couple different ways. All right. So if I can dissolve 5 grams in 100 grams, then how many can I dissolve in 200 grams? And just do it that way. All right. And do like a cross multiplication. Or like for me, I just realized, well, 200 is twice 100. So if I can dissolve 5 grams in 100, that means I can dissolve 10 grams of KClO3 in 200 grams of water, just because it's double. So if I have double the amount of solvent, I should have double the amount of solute able to dissolve. Okay, so I want you guys to go ahead and try to answer these next 3 questions on your own. All right, so just go ahead and try to answer them on your own. And then after you've paused the video, try them out, see if you can do them, and then rewatch the video and I will go through them in just a minute. So pause your video now. Okay, so hopefully you guys actually paused your video and worked through those problems and tried them out on your own. So now I'm gonna go ahead and go through them real quickly. So This one says the solubility of which two salts is identical in 100 grams of water at 95 degrees Celsius. So basically we're looking for where two salts like intersect in their graph at 95. So I would just come to 95 and look along my graph until I find a point where two intersect. And it looks like it is KCl and KClO3. That are intersecting there. Now then, my next question is, which graph has the most rapid increase in solubility if 100 grams of water is heated? All right, so if I'm looking for the most rapid increase in solubility, guys, remember my lines represent the solubility there. So if I'm looking for the most rapid increase, I'm looking for the steepest slope because my lines represent solubility. So my steepest slope is definitely KNO3. And then finally, our last one. So this one, I guess we probably didn't work one of these before, but they're pretty simple, pretty easy. So it says if 50 grams of NH3 is placed in 200 grams of water at 10 degrees Celsius, is the solution unsaturated, saturated, or supersaturated? So once again, we have that 200 grams of water instead of 100 grams of water. So we need to figure out how much it would be. So if I have 50 grams and 200 grams of water, means I can have X in 100 grams. Solve it, and you should get that it would be 25 grams of NH3. All right, so now then we'll use that on our graph. So at 10 degrees Celsius, I have 25 grams of NH3. So what I'm looking at is that above my line, below my line, or on my line? You can already rule out it's not on my line because it doesn't intersect with any lines there. The NH3 line is all the way up here, so that is well below my line. So that would be a unsaturated solution. Just because it is below the line. I'm going to say below the curve since that's technically what it is. Okay. So unsaturated because it's below the curve. So we have not dissolved our maximum amount. So it's an unsaturated solution. Okay, guys, there's going to be plenty of practice on Canvas for you guys. There should be a whole worksheet with quite a few problems just reading these graphs. So I would highly encourage you guys to do that because it's pretty easy, but just making sure you know when it says 200 grams and just making sure you know how to read all of the graphs because they're pretty easy for the most part. All right, so we kind of hinted earlier, we talked about how gases are affected by temperature and pressure, all right, whereas solids are just affected by temperature. So I do actually want to kind of go ahead and define how it affects gases. So for gases, as the temperature of a solution increases, the amount of gas that it can retain is going to decrease. So as I increase my temperature, it's going to decrease the amount of gas it can retain. So this would be like a soda. Soda goes flat when it's warm. All right, so if you've ever heated a soda accidentally or left it out, whatever, it'll go flat. At a given temperature, all right, the solubility of a gas is going to be inversely proportional to the amount of gas above the liquid. So what this basically is telling us is that the greater pressure we have, all right, the more we're going to be able to dissolve of a gas. So the higher the pressure, the greater the solubility of a gas. I always think about this as like if you leave the bottle off, or not the bottle, you leave the lid off on a Coke bottle, all right, the solubility is going to decrease. And eventually your Coke is going to go flat. So like leaving the lid off of a Coke. All right, because you're releasing that gas that was above the Coke bottle, the vapor pressure that's there. All right, it's going to be able to like undissolve because it's the less gas you have up there, just the less solubility you have, the less pressure. All right, and the last thing we're going to talk about real quickly is the rate of dissolution. So basically, rate of dissolution just tells me it's the rate at which a solute is dissolved into a solvent. So how quickly does something dissolve? All right, we can actually manipulate the rate of dissolution. So we can increase it in 3 different ways. All right, and we kind of have a little phrase. So stir it up, heat it up, crush it up. All right, so if I am stirring it, I basically am increasing collisions between my solute and my solvent. The more they collide, the more likely that my solute is to dissolve. So increasing it by collisions. Now, if I heat it, then I am increasing my kinetic energy. So I'm increasing my kinetic energy, which is once again, so that means my particles are moving more. So once again, I'm also going to be increasing collisions there. So if they collide, my solute can dissolve. And then the last thing I can do is I can crush it up. So when I crush it, I'm increasing the surface area. So this is like the difference between dissolving a sugar cube versus like a sugar packet where the sugar is broken up. So it's going to take longer to dissolve a sugar cube than it is to dissolve that individual sugar packet just because it's got a greater surface area. Some more collisions can happen because we have that greater surface area. So increasing surface area is going to cause it to be able to dissolve more quickly. All right, guys, so there should be plenty of practice on Canvas. So you guys will definitely complete those. That's a good place to start to make sure you understand this, but feel free to reach out to Mr. Oglesby or I if you have any questions.